Well, you coming? Yeah, you can tell by the barnacles that water gets up to about this level. So where I'm standing right now is about head deep in water at high tide. I'm so glad I got out of there in time.
Coastal peoples have been observing this rising and falling of the waters for millennia, and most cultures have figured out that the timing of it has something to do with the passing of the moon. But beyond that, there are a lot of questions to explore. Well, let's start with why are there tides in the first place, and what does the moon have to do with it? And why are there two tides a day? And why are there tides in oceans but not in lakes or ponds or, let's say, a glass of water? Some of these questions are best answered from an astronomy point of view, influences from the cosmos, and others will be easier to answer from an Earth-based point of view. So we'll start with the astronomy. Most people think of the moon as orbiting the Earth in a nearly circular orbit, but that's not entirely accurate. Imagine you're swing dancing and trying to have your partner orbit you. There's really no way to do that without leaning back or getting pulled off center yourself. So the moon and the Earth are really actually orbiting a common center of mass called the barycenter. So both objects are spinning around each other. Let's switch to a three-dimensional view of that situation, with the vertical red line passing through that barycenter between Earth and Moon. And because the Earth is so much more massive, of course, that center is much closer to the Earth and actually falls within the Earth. But the Earth is still definitely wobbling around that line. And this also shows a simulation of the waters surrounding the Earth, so as if it had a very thick ocean. And to take the dancer analogy a step further, you might notice as you're swinging your partner that your arms are being pulled towards your partner, but maybe your hair is being flung out the back exactly opposite the direction of your partner. And this accounts for the bulge on each side of the Earth of this simulated water. And meanwhile, the Earth is rotating beneath these bulges that are facing the moon and away from the moon, so that each part of the Earth passes twice in one rotation through one bulge or the other. So this accounts for the two different high tides. And at 90 degrees to that, what's shown as a green band in this simulation would be the low tide, where the water has come from to fill those bulges at either end of the Earth. This is also often explained using Newton's law of gravitation, whereby the nearer side gets a stronger pull from the moon than the Earth does, and the far side of the oceans get a weaker pull of gravity. But hey, I'm a dancer. I like that analogy. It's also important to note that this is a very subtle effect compared to, say, the weight of water due to Earth's gravity. And it's happening on sort of a continental scale, which explains why, your coffee in your coffee cup doesn't get sucked up into the atmosphere as the moon passes overhead. And there's not a noticeable tidal effect in a swimming pool or a lake. In fact, the only reason we notice tides in the oceans is because they are so vast and connected, so that when the weight of water is ever so slightly alleviated by this effect in one region, more water is able to flow into that space from other regions. Consider this analogy where the pressure is alleviated slightly on one region of the water bottle while pressure is maintained around the periphery. Even if it's pretty subtle, there'll be a tendency to bulge up in the middle region. So, there you have the very most basic reason that tides exist in the oceans. Of course, the Earth is not a uniform sphere completely covered in water. It has continents and coral reefs and island chains. And the moon is not the only object in the sky that will influence what happens on Earth. There are over 100 other factors that have measurable influence on the tides. So let's take a look at least some of those. Here we are with the tide chart for June in Newport, Oregon. And this chart happens to have the phases of the moon listed on it too, which is handy. So a few things to notice. First of all, you can see high tide is about 8 feet above reference level. There's a low tide that's actually below zero. It's called a minus tide. And the next high tide is not quite as high. It's only between 4 and 8 feet. There's a low tide that's not really that low at all. And then another high tide, another low tide, another high, another low. So from one day to the next, every other high tide is relatively close in height. It changes slightly, but from one high tide to the very next high tide might be very different in height, and this to the next. And one low tide to the next low tide might also be very different in height. Let's step back out into space for a minute and look at the tidal bulge simulation we've got. I think Australia is a good reference point here. You can see it passing right under the tidal bulge that's towards the moon. But if we change the view to look at the other side of the Earth, the bulge that's opposite the moon, we can see that Australia is passing well below that bulge this time. So while it might be passing under the piled up water that's pulled towards the moon, the bulge that's opposite the moon theoretically will not experience quite as high a high tide as it passes through that point. The other thing to notice on this chart is that you see when it's quarter moon, the high tide's it's under 8 feet. The low tide is nowhere near zero. The high tide is not that high. The low tide's not that low. But they get more extreme from each other. When we come to the full moon here around June 13th, notice the high tide is actually quite high. It's up around 9 feet. The low tide is actually negative a foot or two. So the extreme between high tide and low tide is quite pronounced here. And by the time we get back to the next quarter moon, sort of in the middle. And then when we get to the new moon, again, we've got high highs, low lows, at least for one of the tides of the day. So this effect of full moon compared to quarter moon, or new moon compared to quarter moon, we'll explore that also. Just as the Earth and Moon are dancing around each other, it's also true that the Sun and the Earth-Moon system are dancing around each other. The Sun is much more massive than the Moon, so you'd expect it maybe would have an even bigger influence, but it is so far away and it's a much slower dance. The effect of the Sun on the tides is only a little less than half as much as the influence of the Moon on the tides. If the Moon didn't exist, we would still experience a tidal bulge facing towards the Sun and another tidal bulge exactly opposite the position of the Sun relative to the Earth. We do have a moon, so that the effects of the moon on the tides and the effects of the sun on the tides will combine. And at some positions, when the moon is exactly between Earth and Sun, the moon will be pulling its tidal waters towards it. The sun will also have a bulge towards it. Those two bulges will add together to make an extra large bulge, a situation called a spring tide. But about a week later, when the moon is perpendicular to the direction of the sun, it's illuminated in a way that we call a quarter moon. And if the moon is pulling water towards itself, and the sun is also exerting an influence that would draw some of that water in the direction of the sun, well, water doesn't know which way to go, and it sort of hangs out. So we get less extreme tides. This situation is referred to as a neap tide. And then a little while later, when the moon is exactly away from the sun, we get the tidal bulge that's away from the sun and the tidal bulge that's towards the moon working in the same direction. This is the full moon, and we're back with another spring tide. And then when the moon is again perpendicular on the other side, we get the other quarter moon, and again the water is getting a mixed message, and it doesn't flow as much one direction or the other. A third major influence has to do with the fact that the moon's orbit is not circular but elliptical, meaning that sometimes it's closer to the Earth and sometimes it's farther away. It goes through this cycle about once every 28 days. When the distance is closest, called the perigee, the tidal influence is exaggerated, and when the moon is at its farthest point, at the apogee, its influence is diminished. A similar effect comes from our Earth's elliptical orbit around the sun, where our closest approach to the sun happens in January, and our greatest distance from the sun is in July. And this acts respectively to exaggerate the tidal bulges and diminish them at those two parts of the year. Now, of course, you're wondering what happens if it's in January and the moon comes into perigee and happens to be a full moon or a new moon, so that all these factors we've discussed so far causing more extreme tides are happening all at once. This is a situation called a king tide, and interestingly, it's a little glimpse about what average high tides might look like in the future as we experience sea level rise. We can mitigate this by following the prescription given by the world's top climate scientists, but we've got to do it soon. The last aspect I want to look at in this astronomical section is the effect of the tilt of the Earth relative to the orbits of the moon and the sun. For some reason, the tilt of the Earth's rotational axis is 23.5 degrees compared to its path around the sun, called the plane of the ecliptic. This accounts for the seasons and the fact that, from our perspective, the sun seems to follow a very high path through the sky at summer solstice, and 6 months later, for the winter solstice, follows a much lower path through the sky, at least here in the northern hemisphere. While the sun goes through this high path, low path cycle just once a year, the moon actually goes through this cycle in just 28 days. This means that the highest the sun ever appears in the sky is 23.5 degrees above the equator, which is defined by the Tropic of Cancer. And you can see that it passes just below the tip of Florida on the continental US. And the farthest south that the sun ever ventures is 23.5 degrees below the equator, which is defined by the Tropic of Capricorn. And as you can see, passes right through Australia and the bottom of Africa and South America. The moon's orbit maintains a 5-degree tilt relative to the plane of the ecliptic, which means it varies a bit relative to the Earth's axis of rotation. This tilt explains why we don't get an eclipse on every full moon and every new moon. In some years, the highest path the moon ever follows is 5 degrees below the Tropic of Cancer, giving it a relatively low path through the sky from our perspective. And in other years, it might get as high as 5 degrees above the Tropic of Cancer, giving it an even higher path through the sky than the summer sun at solstice. And furthermore, the orientation of this 5-degree tilt slowly rotates as the Earth-Moon system orbits the sun. Don't make me go into the details of angular momentum and torque, but suffice it to say that it's the same principle that makes gyroscopes do weird things when you swing them around. It takes about 18.6 years for that orientation to spin all the way around, which means the tide chart from 2019 looks almost identical to the tide chart from the year 2000, 19 years earlier, when all the astronomical conditions are kind of reset and then just run like clockwork, same way they did the last time. Let's see how this affects the tides, at least in theory. At this point in the simulation, the moon is on the side of the Earth that's tilted towards the moon. This is when North America is about as close as it's going to get to passing right under that tidal bulge that's towards the moon. And notice that the bulge that's away from the moon is far below the equator and far from North America. As the moon continues in its orbit at perpendicular to the tilt of the Earth, the equator is passing right under the moon, or the moon tends to be right in the middle. And as it passes to the side opposite the northern tilt of the Earth's axis, notice that this is when we are, the side towards the moon is farthest away from North America for that theoretical bulge. But on the other side, the bulge that's opposite the moon is when North America would be passing closest to it. And yet, if we look back at the tide chart from June, which is pretty close to the summer solstice, when the sun is highest in the sky, that's when the summer full moon would be lowest in the sky. So around midnight on the full moon, when we would expect a very low passage, we see probably the most extreme tide of the entire month. And then half a day later, when the secondary bulge is passing, by my model, I would expect the highest high tide at that point, but we get a high tide that's not really that high at all. So something's not quite right about that model. And we will see in part 2 that there are a lot more complicating factors. To understand the actual tides on a planet like Earth, we need to take a closer look at things like wave interactions, resonance, collisions, and various other constantly changing conditions. To do this, let's take a perspective down here on the solid Earth, and we'll treat the moon and the sun as objects passing over us in the sky, exerting some gravitational influence. From this perspective, we can even treat the secondary bulge that's opposite the moon and the bulge opposite the sun as if they were a second moon or a second sun, exerting a similar influence as those actual bodies. Let's start by looking at the very simplest model I can think of, which is a spring tide with both sun and moon directly above the equator. There would be two tidal bulges moving from east to west, following the sun and the moon. The red in this represents high tide, blue represents low tide. And you can see it would just go around if there were no friction, no continents, deep water ocean all around a uniform sphere. This is what it would look like. Spoiler alert, This is not what the actual tide looks like. Here is a simulation from satellite imagery of the actual tides in the Western Hemisphere over one 25-hour period. Again, the red represents high tide and blue represents low tide. Here's another simulation based on satellite imagery, flattened out, so you can see the whole Earth's oceans. In this one, the white represents the high tide and black represents the low tides. And you can see it's much more chaotic than a simple bulge or pair of bulges moving from east to west. In fact, you might notice some rotational behavior here, which we'll talk about momentarily. The island of New Zealand in this is in the lower middle, slightly left, and you'll notice some interesting behavior around it, where it's high tide on one side and low tide on the other, and just kind of constantly swirling around. Let's start with the concept of wave interference, whereby two waves may be traveling in different directions, encounter the same space at the same time, and interact with each other either constructively, where they add together and get a bigger resulting wave, or it could be that they interfere destructively, where, say, the trough of one wave meets with the crest of a different one, and the waves kind of cancel each other out. Also notice that when a wave encounters a solid barrier like a cliff, it essentially gets reflected back out as an outgoing wave that can then interact with the incoming waves or continue on, might even go right through them and keep going. With these factors in mind, let's consider a closed basin like a bathtub. If I cause a wave, it can bounce off the far end of the tub, come back, bounce off this end, and reflect. You can see how these waves are reflecting back and forth. And if I time it with the reflected wave and create a new one, I get what's called resonance, and we get a pretty sizable disturbance. If left alone, that sloshing would eventually just settle out and stay calm. But just like pushing someone on a playground swing, if there's a periodic force, even a subtle one, if the timing is just right, that can be enough to keep the resonance going. If we have a collection of basins of different sizes, shapes, and depths, but all subjected to the same periodic force, they will respond differently based on the timing it takes to do the reflection and reflect back. So some may resonate and others may not. This is essentially what's going on with the various ocean basins. Looking at a map of the world, we think we have a pretty good idea of the size and shapes of each of the oceans. But as far as this tidal sloshing is concerned, the ocean depth makes a difference. And in fact, the continental shelf boundaries are more significant than the actual continental shorelines themselves. If we take the famous Bay of Fundy, for example, which is connected to the Atlantic Ocean, you can see that it's part of a continental shelf in North America. And this sub-basin has a natural sloshing frequency of about 13.3 hours, which is very close to the pulse from the moon cycle, which is about 12.47 hours, which accounts for its record-setting 50-foot difference between high tide and low tide. Each of these sub-basins within the world's oceans are responding in their own unique way to the rhythm of the passing of the moon. And of course, they're interacting with each other. But there's a little bit more physics to be understood here. Because the Earth is a rotating sphere with a greater circumference at the equator than the poles, any large-scale north-south movements will experience something called the Coriolis effect, which is the same phenomenon that causes hurricanes to spin clockwise in the southern hemisphere and counterclockwise in the northern hemisphere, so that what may start out as a back and forth movement soon becomes a circular movement. These various cells within the oceans are called amphidromic systems, from the Greek word meaning circling around. Researchers have mapped out these cells, and they're centered around what are called amphidromic points. So the one closest to the Pacific Northwest here is off the coast of Baja California, and it rotates counterclockwise so that over time high tide will sweep through Los Angeles and up the west coast and eventually up onto Canada and through Alaska. And then the low tide will sweep through a little while after that. The east coast of the United States is affected by two different amphidromic systems, one in the North Atlantic and one down in the Caribbean, and the interaction of the two together might determine what's going on along the east coast of the US. All this makes for some very interesting and complicated behavior that may or may not coincide with the passing of the moon directly overhead. In fact, if we think about New Zealand again, it's impossible that both the high tide and the low tide could happen when they're supposed to relative to where the moon is passing. And yet it is still the rhythm of the passing moon, if not the immediate location of the passing moon, that's driving most all of these systems. This complexity leads to very different tidal behavior at various coastlines around the world that typically fall into three categories. I gathered tide charts from 2 weeks in early September 2022 from various locations to compare. This one is from Galveston, Texas, on the Gulf of Mexico, and you can see that for part of the weeks it's got just one high tide and one low tide per day. This is a pattern called diurnal or daily tides. But notice in those middle days it has two highs and two lows a day. These are called semi-diurnal tides, which are pretty typical of the west coast of the United States. We see a similar pattern off the coast of Japan. Here's the same 2 weeks in Newport, Oregon, which we've kind of looked at earlier. This is semi-diurnal, but with a different high tide and low tide for the different semi-daily tides. This is called semi-diurnal mixed. New York City has a semi-diurnal tide, but it's pretty much the same high tide and low tide both times of the day. So this is just semi-diurnal but not mixed. Here's the chart for Avonmouth in England, and you can see the spring tides and neap tides, but almost no difference between the two daily high tides. So this is just semi-diurnal. Here's a chart from a port in Italy on the Mediterranean Sea that I include mainly because the scale, if you look, there's less than 1 foot between high tide and low tide, which kind of makes sense if you think about the Mediterranean being connected to the Atlantic, but only by a very narrow channel, the Strait of Gibraltar. So not a whole lot of water can flow in and out twice a day. For boaters, these currents associated with the tides are vitally important. Let's consider the Puget Sound and the San Juan Islands up near Seattle. As the tide rises in the Puget Sound, as shown by this chart over on the right, water has to come from somewhere to fill up the sound and all the other coastal bays and inlets along that coast. It's a rather complicated maze of channels and islands, and we'll notice that when the tide is at its highest, most of those channels have minimal current. This is called a slack tide. This is also true around low tide, when it's not changing very rapidly, also a slack tide. But when the tide is in the middle, it's changing the most rapidly. That's when we get the strongest currents, and sometimes there's a slight time delay at certain locations. It's not just the height of the water that affects boaters, but the rate of change in the height of the water. Okay, now for some wonderfully strange aspects of tidal behavior. Starting with what's called a tidal bore. There are about 60 places on Earth where the tidal behavior and the local geography combine to make the incoming tide, especially on a extreme tide like a spring tide, come in as a single giant wave front. The most famous of which is called the Silver Dragon on the Qiantang River in China. Adventurous surfers can even ride this wave for about 7 miles as it comes rushing in from the sea twice a day. Of the hundreds of factors that have a measurable effect on the tide, there are about a dozen predictable ones that account for 90% of tidal behavior, about 90% of the time, and are usually accurate to within several inches of the actual tide. Some of these are astronomical in nature, as we discussed in part 1, and others rely on a network of monitoring stations around the world to track historical data. There are only 3 of these along the Oregon coast, with the closest one to Eugene being in Waldport in the Alsea Bay. This combination allows for the production of tide charts even years in advance. But there are other factors that are not predictable, including wind, river flooding, and storm surges, as with hurricanes, where the ultra-low pressure system created by the storm can draw up a bulge of water, much like the moon can, but on a somewhat smaller scale. All of these can significantly affect the level of seawater along the coast, so don't rely solely on a tide chart as conditions change. Well, I hope you've found this topic as interesting and informative as I have. Be careful out there. Please click on the resource links below if you're interested in learning more details about any of this. Feel free to contact me if you have further questions or if you have information you think I might be interested in. Keep on exploring and seeking to understand.